Right now, tens of thousands of people live on top of the hardened remains of a Mount Rainier mudflow that traveled roughly 60 miles to Puget Sound. That sentence sounds like a disaster movie. It is actually geology. Rainier is the white peak on Washington's horizon, the mountain people photographed from highways, office windows, and airplane seats. At 14,410 feet, it looks permanent, untouchable, almost too beautiful to be dangerous. Yet the greatest volcanic hazard at Rainier may not be lava, ash, or an enormous eruption. It may be a lahar, a fast, dense flow of water, rock, ice, and mud that can sweep down a river valley like wet concrete. The unsettling part is simple. A large lahar could begin with a landslide, not an eruption. There may be no glowing crater, no dramatic ash column, no long countdown on the evening news. A mountain can be quiet and still be hazardous. And models suggest that a flow from the upper slopes could reach populated areas outside the park in roughly 15 to 60 minutes, depending on its route. That is the number we will keep coming back to, because it turns a distant geological possibility into a problem measured in minutes. To understand why Rainier deserves more attention than the volcano in the movies, start with the mountain everyone already knows. Yellowstone is famous for a good reason. Beneath the national park is a vast volcanic system that has produced enormous eruptions in the distant past. The word supervolcano carries a sense of planetary scale, and the images attached to it are hard to forget: continent-wide ash, darkened skies, civilization-sized consequences. But danger is not determined by spectacle alone. Yellowstone is surrounded by broad stretches of wilderness and relatively sparse population. Its largest imaginable eruption would be extraordinarily destructive, but the probability of that particular event occurring during any one human lifetime is considered very low. Scientists monitor Yellowstone continuously, while also making clear that it is not an immediate reason for public panic. Rainier presents a different calculation. It is not necessarily more explosive than Yellowstone. It is more exposed to people. The mountain stands southeast of the Seattle-Tacoma region, above river valleys that connect glaciers to towns, roads, rail lines, utilities, and the port of Tacoma. Communities including Orting, Sumner, Puyallup, and Auburn occupy areas where past volcanic flows left thick layers of sediment. Some of those deposits are thousands of years old, others are much younger in geological terms. That is the key distinction. Yellowstone is the larger cinematic story. Rainier is the closer, more local hazard. Rainier belongs to the Cascade Volcanic Arc, created as the Juan de Fuca tectonic plate moves beneath North America. Water and other fluids released from the descending plate help melt rock deep below the surface. Some of that magma rises, feeding volcanoes along the range. The process is still active. Rainier is not an extinct mountain that merely happens to have a crater. It is an active volcano with a long record of eruptions and landslides, even though its last known eruption was centuries ago. That quiet interval can be misleading. Human memory measures time in generations. Volcanoes measure it in layers of rock. Rainier is also unusually well supplied with the ingredients that make lahars possible. Snow and ice cover its upper slopes. Loose volcanic material surrounds the summit, and in parts of the mountain, hot, chemically active fluids have altered strong rock into weak, clay-rich material. You do not need the biggest possible eruption to create a destructive flow. You need gravity, water, sediment, and a route downhill. Rainier has all four. The mountain's beauty is not separate from the hazard. The glaciers and steep valleys that make the landscape spectacular are part of the system that can turn a collapse into a long-distance flow. A lahar is not simply a flood with a little mud mixed in. It is a moving mass of water, volcanic rock, clay, ice, trees, and whatever else the flow tears loose along the way. At Rainier, past lahars have traveled at roughly 45 to 50 miles per hour and reached depths approaching 490 feet where they were confined in narrow valleys. That is not a river slowly overflowing its banks. It is a dense, destructive current with the ability to carry boulders, trees, vehicles, and buildings. Think of ordinary floodwater. It can push a person off balance. Now add enough rock and sediment to make the flow several times denser, then send it through a valley that naturally funnels the material forward. The result behaves less like water and more like a moving wall of concrete. Lahars can also grow as they travel. A collapse high on the mountain may begin with a mixture of rock and ice. Once it enters a river channel, it can absorb loose soil, old volcanic deposits, trees, boulders, and water already moving downstream. The flow becomes larger and more fluid at the same time. That process matters because the material leaving the mountain is not necessarily the material arriving at a town. A relatively small-looking landslide at high elevation can transform into a much larger event miles away. Now consider the paths. Rainier's glaciers and high slopes feed several drainages, including the White, Puyallup, Nisqually, and Carbon river systems. These valleys do not end in empty wilderness, they lead toward developed lowlands. The greatest volcanic danger, according to the U.S. Geological Survey, is therefore not the image most people carry in their heads. Lava is dramatic, but lava flows at Rainier would generally be limited to the upper mountain and nearby parkland. Ash could disrupt transportation, water supplies, agriculture, and daily life over a much wider area. But it is not the same physical threat as a concrete-like flow charging down a valley. A lahar follows the landscape. It uses the valleys as channels and then spreads across flatter ground. By the time it reaches communities, it may have slowed, but slowing does not make it harmless. The material can harden into thick, rock-like deposits that bury roads, buildings, bridges, and entire sections of infrastructure. There is no practical way to build a wall around a mountain-sized flow. The central defense is evacuation. That changes the question from how big could the eruption be to how quickly could people move out of the channel. The answer depends on where the flow begins, which drainage it enters, how fast sensors detect it, and whether residents act immediately. For the closest communities, the margin is not measured in days, it is measured in minutes. The hardest part of understanding Rainier is that the danger is hidden inside a familiar view. Imagine standing in a town beneath the mountain on an ordinary weekday. The peak is bright with snow, traffic is moving, children are in school, someone is walking a dog beside a river that looks completely normal. Nothing about that scene announces volcanic hazard. Now look at the mountain as a geologist would. It is nearly 3 vertical miles high. Its upper slopes hold enormous quantities of snow and ice. Its lower flanks are cut by steep channels that can guide water and debris far beyond the park boundary. The ice is part of the visual identity of Rainier. It has also stored water at elevation. The rock creates the second half of the problem. Rainier is built from layers of lava, rubble, and older volcanic deposits. Near the summit and on parts of its flanks, volcanic gases and heated groundwater have reacted with the rock for thousands of years. The chemistry can leach away stronger minerals and replace them with clay. That process is called hydrothermal alteration. It does not turn the entire mountain into paste. It creates zones of weak, water-rich material inside an otherwise massive volcanic edifice. A useful comparison is a stone building with sections of mortar that have slowly become soft. From across the street, the structure still looks solid. Under the right force, the weakened parts are where failure can begin. The past provides the scale. The Osceola Mudflow, about 5,600 years ago, involved an enormous collapse from Rainier's summit and northeast flank. The event mobilized roughly 2 to 3 cubic kilometers of altered volcanic material and spread across about 212 square miles of the Puget Sound lowland. That deposit now lies beneath places that are not empty. Orting, Buckley, Sumner, Puyallup, Enumclaw, Auburn, Kent, and areas near the port of Tacoma include land affected by the Osceola flow or later lahars. Then there is the Electron Mudflow, roughly 500 years ago. It began as an avalanche of altered rock on Rainier's west side and traveled about 60 miles to the lowland. When it reached the community of Electron, the deposit was about 98 feet deep. You can visit a modern town and still be standing on the remains of an ancient flow. The landscape looks settled because the disaster has already happened there once. That is why maps matter more than appearances. Rivers do not care whether a valley contains a farm, a school, or a subdivision. If the terrain carried a lahar before, it may carry one again. And the most important question is not whether Rainier has made these flows in the past. The rocks have already answered that. The question is what could make the next one move. There are several ways to create a lahar at Mount Rainier. An eruption can melt snow and ice or destabilize the upper slopes. A sudden release of water from a glacier or a rainstorm can mobilize loose sediment, and a large landslide can dump weakened volcanic rock into a drainage where water transforms it into a rapidly moving flow. The last mechanism is the one that breaks the usual mental picture of a volcano. When people imagine an eruption, they imagine signals. Earthquakes, swelling ground, changes in gas, steam, or visible activity. Those signs can occur when magma is rising. A landslide caused by structural failure is different. The collapse may begin without a recognizable buildup that instruments can detect in advance. The USGS describes large landslide-generated lahars at Rainier as capable of occurring without precursory activity. That does not mean every future lahar will arrive without warning. An eruption-related event might provide substantial signals. It means that one important pathway begins only after material is already moving. Here is the chain. First, a section of weak, clay-rich rock fails on a steep flank. The initial avalanche accelerates downhill under gravity. It encounters snow, ice, surface water, and loose sediment. The material becomes saturated and loses much of its internal friction. A slide begins to behave like a fluid. Next, the flow enters a channel. The valley concentrates its energy and gives the material a route toward lower ground. Along the way, the flow erodes its banks and picks up more sediment. Its volume increases. Its front can remain fast and dense even as the flow stretches behind it. Finally, the lahar reaches the lowlands. The slope decreases. The flow spreads sideways, slows, and deposits its load. That is when the destructive material may cover the greatest area. Computer models of a landslide similar to the Electron event show why emergency planners focus on timing. Depending on the source area and route, a lahar could reach residential areas inside the park in about 5 minutes and populated areas outside the park in roughly 15 to 60 minutes. Those figures are not a prediction of a specific future event. They are travel time estimates for modeled scenarios. The exact result would depend on the size and composition of the collapse, the drainage it entered, the amount of water available, and the shape of the valley. Still, the practical conclusion is clear. Once a large lahar begins, people downstream may not have time to study the situation, wait for a second message, or drive casually away. The route to safety is usually higher ground, often reached on foot. Roads can clog. Bridges can fail. A car may place someone directly in the same channel the flow is using. The mountain does not need to chase anyone, it only needs to send material into the right valley. Rainier's most startling story is written in its deposits. The Osceola Mudflow was not a minor slope failure. About 5,600 years ago, a huge section of the summit and northeast flank collapsed during a period that included eruptions. The collapse left a horseshoe-shaped crater about a mile wide and sent altered volcanic material down the White River system. The flow crossed the lowlands and reached Puget Sound. Its deposits covered a broad area, extending toward present-day Kent and the site of the port of Tacoma. The mountain that exists today is partly the result of what happened after that collapse, including later lava that filled much of the scar. A mountain can rebuild. A city can also build on the old debris. The younger Electron Mudflow is even more revealing because its beginning cannot be confidently tied to an eruption. Around 1500, an avalanche of hydrothermally altered rock came from the west side of Rainier. Scientists have proposed several possible triggers, including a small eruption, a hydrothermal explosion, or an earthquake, but the deposit itself contains no clear evidence of associated eruptive activity. Whatever started it, the material was weak, wet, and mobile. The resulting lahar moved about 60 miles downstream and entered the Puget Sound lowland at a depth of roughly 98 feet near Electron. That is the turn in the story. The mountain's hazard is not limited to an eruption scenario. The word "without warning" needs precision here. Scientists cannot say that every landslide would be invisible, and monitoring systems can detect some flows after they begin. The point is narrower and more serious. A large flank collapse may provide little or no conventional volcanic warning before the collapse itself. The comparison with Mount St. Helens helps put this in context. On May 18, 1980, the St. Helens eruption produced devastating landslides, pyroclastic flows, ash, and lahars. Snow and ice melted or were mobilized, and debris-filled water rushed through river valleys. The event demonstrated how quickly volcanic material can become a regional flood of rock and mud. Rainier is not Mount St. Helens. Its eruptive behavior, geography, and hazard pathways are different, but Rainier has far more permanent snow and ice than St. Helens had before its 1980 eruption, and its lower valleys connect to a densely developed metropolitan region. The comparison is not a prediction. It is a reminder that lahars are not theoretical objects. They have been observed, mapped, modeled, and studied after destroying communities. The most painful example happened far from Washington. In November 1985, the Colombian volcano Nevado del Ruiz erupted. The eruption melted snow and ice near the summit, sending lahars into downstream valleys. One of them reached the town of Armero at night and killed more than 20,000 people. Armero became a defining case in volcanic risk science because the danger was not unknowable. Hazard maps existed. The volcano had shown signs of unrest. Warnings had been issued, but communication, decision-making, and evacuation failed to produce a timely response. The comparison to Rainier must be handled carefully. Nevado del Ruiz and Rainier are not identical volcanoes. Their ice, slopes, drainage systems, monitoring networks, communities, and emergency institutions differ. What they share is the physical behavior of a lahar. A flow can travel quickly through a valley, arrive at night or in bad weather, and destroy structures that remain perfectly normal until the moment the material reaches them. Armero also exposes the human side of the problem. A warning only works if people receive it, recognize it, trust it, and know exactly where to go. A map on a website is not the same as a practiced route. A siren is not useful if residents assume it is a routine test. Washington has spent decades trying to avoid that failure. A Lahar warning system for the Carbon and Puyallup River valleys became operational in 1998 through cooperation among the USGS, Pierce County, Washington Emergency Management Agencies, and other partners. The system uses acoustic flow monitors and tripwires. Buried sensors detect the distinctive ground vibrations produced by moving debris. Automated systems analyze the signals and alert emergency centers. The public warning side uses multiple channels, including sirens, emergency alerts, broadcast media, and local communication networks. In places such as Ording, schools and community organizations have practiced evacuation routes repeatedly. The goal is not to outrun a flow, it is to reach high ground before the flow arrives. That preparation is a major improvement over the conditions that existed in Armero. It does not eliminate the hazard. Detection begins after movement. A sensor can provide valuable time, but it cannot guarantee an early forecast of the collapse itself. The closer a community is to the source, the smaller the remaining window may be. This is why the warning system is designed around immediate action. Residents in at-risk valleys are told to move as soon as they receive a Lahar warning or hear the characteristic prolonged rumbling and roaring of an approaching flow. Traffic is not the primary plan. Waiting for confirmation is not the plan. Climbing is the plan. The pushback against disaster storytelling is that rare hazards can be exaggerated. That criticism is fair when a script presents a possibility as an imminent event. Rainier is not currently a reason for mass panic. A large lahar is an infrequent hazard, and no one can identify its exact date. But rarity does not make a mapped valley safer. It makes preparation easier to postpone. The risk is real. The timing is not known. There is also a difference between warning and prediction. Prediction would mean identifying the exact day and route before the slope fails. The existing system is not designed to do that. It is designed to recognize a moving flow, send the message quickly, and give people a chance to leave the channel. That may sound like a modest goal, but in a fast-moving geological emergency, converting even a short interval into an organized response can determine who reaches safety. So what is actually established rather than merely imagined? First, Rainier is an active volcano with a documented history of eruptions, landslides, lahars, and smaller debris flows. Second, its upper slopes contain abundant ice and areas of hydrothermally altered rock. Third, geological deposits show that large flows have reached the Puget Sound lowland repeatedly. USGS researchers have identified evidence for at least 9 large Rainier lahars reaching the lowlands during the last 5,600 years. Most large events occurred during eruptions, but the Electron Mudflow shows that a major lahar can also begin with a flank collapse not clearly associated with eruptive activity. Fourth, the affected corridors are developed. They contain homes, schools, highways, bridges, rail lines, pipelines, utilities, and port facilities. The hazard is not confined to a remote national park trail. Fifth, the flows can move with extraordinary speed and depth. Past lahars traveled at about 45 to 50 miles per hour and reached nearly 500 feet deep in confined valleys near the volcano. Those numbers describe past deposits and observed geological evidence, not a promise that every future event would match them. The concrete achievement is the response system. Monitoring stations watch the volcano and its drainages. Acoustic flow monitors listen for vibrations from moving debris. Tripwire systems add another detection method. Emergency officials can send alerts through sirens and other channels. Evacuation routes direct people toward high ground, and schools practice so that the response is not invented during the emergency. The system has also been modernized. Newer stations can transmit data in real time and incorporate seismometers, infrasound sensors, cameras, GPS equipment, and other instruments. Expanded monitoring is intended to improve detection across more drainages and provide better information about a flow's location, speed, and size. That is not a movie solution. It is better, a practical system built around the actual physics of the hazard. The system cannot stop a lahar. It cannot hold up a weakened flank. It cannot protect every building in a valley. What it can do is turn a geological event into an evacuation problem, which is a problem humans have at least some ability to solve. A person on high ground is difficult for a lahar to reach. A person in a channel is not. The flow also changes the meaning of distance. A town can be dozens of miles from the summit and still be connected to it by a river channel. The mountain does not have to send debris in a straight line. It only has to send it downhill while gravity and water do the navigation. That is why a community can feel far away from the volcano and remain directly exposed to its most mobile hazards. That difference is the payoff of preparation. It is also why drills can look excessive until the day they are not. Preparedness also protects against confusion. People may hear a siren and assume it is a test, a fire alarm, or a routine public warning. Practice gives the sound a specific meaning. The response becomes less dependent on a perfect announcement and more dependent on a habit. Move uphill, leave the channel, and keep going until the terrain is clearly above the modeled flow path. In that sense, the most advanced piece of equipment may still be a community that knows what the first alarm means. The next chapter is not about predicting a date. Volcano science cannot provide one. It is about improving the few decisions that matter when the clock starts. Researchers continue to map deposits, monitor earthquakes and ground movement, study gases and hydrothermal systems, and model how different landslide sizes could travel through the Puyallup and Nisqually drainages. The goal is to understand not only where a lahar might go, but how deep it could become, how quickly it could arrive, and which locations might remain above the flow. The modeled travel times explain why emergency planners emphasize routes to high ground instead of relying on highway evacuation. In some scenarios, residential areas inside the park could be reached in about 5 minutes. Outside the park, modeled arrival times range from roughly 15 to 60 minutes, depending on the source and pathway. For a person watching the mountain, 60 minutes sounds substantial. For an entire community, it is not. Alerts must be detected and transmitted. Sirens must be heard. Residents must understand that the message is real. Children must leave classrooms. Workers must stop what they are doing. People must move without creating a traffic jam that traps them in the valley. A warning is therefore a coordination problem as much as a technical one. The first residents who hear the alert may be moving while others are still deciding whether the message applies to them. Schools, workplaces, visitors, and drivers may all be reacting at once. Clear routes and repeated practice reduce the chance that thousands of people make the same wrong choice in the same narrow corridor. That is why evacuation drills matter. Repetition reduces the number of decisions people have to make under stress. You do not want to search for a route while the warning is sounding. You want to know which direction leads uphill before the warning exists. There is another complication. The mountain is changing, as all glaciers and volcanic slopes do. Ice retreat can expose new rock and alter the amount and location of sediment available to streams. Smaller debris flows already occur on Rainier, often from glacier melt, intense rainfall, or sudden releases of water. Most remain within the park, but they provide scientists with ongoing information about how the landscape responds. Those smaller events should not be treated as proof that a catastrophic lahar is imminent. They are evidence that the mountain's surface is active and that water continues to reshape its channels. The public challenge is psychological. Slow, rare hazards compete poorly for attention. A spectacular eruption has a clear image. A weakened flank beneath a snowfield does not. People also adapt to beautiful places. A view becomes part of the commute. A warning siren becomes background noise. A hazard map fades behind newer concerns. The mountain remains visible, but the reason for the evacuation route becomes easier to forget. Scientists cannot remove that human tendency. Emergency managers can counter it with education, drills, signs, monitoring, and clear instructions. The best outcome is not a dramatic rescue. It is a quiet evacuation that turns out to have been unnecessary because the alarm was triggered by a smaller event or a system test. The worst mistake would be treating uncertainty as reassurance. Rainier may remain quiet for centuries. It may eventually produce an eruption with substantial warning, or a large landslide may happen with little conventional volcanic buildup. These possibilities are not equally likely at any given moment, and none supplies a calendar date. What they share is a requirement. People in the valleys must be ready before the mountain gives them a reason. Return to the number from the beginning, 15 to 60 minutes. That is not a countdown to a known eruption. It is the modeled travel time for certain large, landslide-generated lahars to reach populated areas outside Mount Rainier National Park. The other number is older, roughly 5,600 years. That is how long ago the Osceola Mudflow spread across the lowlands. A third number is much younger, about 500 years, the approximate age of the Electron Mudflow, which traveled around 60 miles after beginning on Rainier's west side. Together, those numbers explain the real story. Yellowstone is not the only volcano worth watching, and it is not automatically the most immediate danger to every American community. Rainier's hazard comes from a different combination: a steep, active volcano, abundant ice, weak altered rock, long river valleys, and developed lowlands downstream. The mountain does not need to look angry. It does not need to glow at night. A postcard can hide a warning written in the landscape. But this is not a reason to fear every cloud near the summit. It is a reason to understand the place where you live. The same science that identifies the hazard also provides maps, sensors, sirens, drills, and evacuation routes. If you live or work in a lahar hazard area, the useful question is not whether you can predict the mountain. You cannot. The useful question is whether you know the nearest high ground, whether you recognize the warning, and whether you can move without waiting for someone else to decide first. Rainier is beautiful because it is alive, shaped by fire, ice, water, and gravity. Those forces created the landscape, and they will continue to reshape it. The mountain is not announcing a disaster today, it is reminding us that quiet is not the same as harmless. The most useful image is not a city disappearing beneath gray mud. It is a classroom, a workplace, or a neighborhood responding correctly to a message that may never come in their lifetime. That is what preparation looks like when the hazard is rare, ordinary people practicing an extraordinary route long before the landscape demands it. When the next warning comes, the people who already know where to go will not need the mountain to explain itself.